where it says that it wants to plot the stresses for a domain X something, Y something. I would assume that would be a contour plot as well.
Which one?
Part A of 1.
Part A of 1. Yes, that's also a field solution. So it's a 2D plot, or a 3D if you consider the solution to be the third dimension. Okay. All right, guys. So we're done with the solution, general solution for elasticity. I like that you consider something. You know, now with that code that you have, you can solve solutions of fractures, of well bores, but also of any other thing that you put in there. So that's a general solution for elasticity. Also, you could modify a little bit your code and say, instead of adding just a simple isotropic relationship, you could modify those coefficients to be anisotropic or to be anything you want. Or you could have those coefficients to vary with location, from location to location, and you could solve a problem of heterogeneous distribution of Young modulus and Poisson ratio. So there are many things you can do in the same problem to solve some type of problems that are not available through analytical solutions. Okay, it's the same thing, it's the same code. All right, so let's talk now about one of my favorite topics, which is poroelasticity. This part in poroelasticity is a summary of a book from this author over here called Olivier Coucy, and it's in chapters 3 and chapter 4. All the people I know that work in poroelasticity, they all go to these equations when they solve poroelasticity problems, because he developed those very nicely. And that book is called let me see if I got the name correct. Okay. Is this one, okay? And some of you already got a PDF copy. If you want a PDF copy, this is being filmed, right? It's going everywhere, right? So you could buy it, or you could find it somewhere else. But it's a very good book, guys. I strongly recommend that. I'm going to follow the derivation from this book. Okay, so before we have been dealing with general continuum mechanics, and we never talked about pores. We just talked about solids without pores. Now we're going to introduce the presence of the pores, and we're going to develop a very robust mechanical framework to analyze the influence of pore pressure in porous solids. So let's imagine our typical represented elementary volume where we have stresses, but now we have pores. And we're going to assume for now that those pores are connected. Probably it's not drawn very well in this schematic, but just imagine that those pores are connected. This is a three-dimensional structure. We have solids and we have pores, okay? And the pores could be filled with a fluid, and inside those pores there can also be a pressure that, for now, let's just call it P. So P is the pressure inside the pores. And the pores, the pressure in the pores can actually modify the size of the pores. If you have higher pressure, probably that pore can get a little bit larger. So in the pores, we have fluids, we have pressure. Can the fluids apply a shear stress on the wall of the pores? No, right? It's similar to the case of the wellbore. The fluids cannot apply a steady shear stress on the wall of the wellbore. So there's going to be no shear. Notice that now we're getting into a field in which the solid deforms, but the pores, they deform too. So in the pores, we're going to have deformable pore walls depending on the pore pressure. And also we're going to define here what it is, a total bulk volume. We used before bulk to compute bulk mass density. So when you say something is bulk, it means that you're just getting an average value of something which is heterogeneous, and you're averaging a quantity just to get a bulk amount. So for the bulk volume, we're going to consider that the original bulk volume, we're going to call it a differential of omega, and we're going to add the sub-index not there to say that that's the original volume. Okay? Everything okay so far? So nothing new so far, other than we have introduced the pores. Here is where we start to apply new concepts, okay? What is the porosity? Let me call, for now, N to porosity, and you tell me what is porosity, what is the porosity of this solid. We know it's going to be a ratio, right? The what? So the void volumes, I'm just drawing a rectangle here, okay? It's going to be the void volumes divided what? Divide the entire volume, which is the summation of the solid volume plus the void volume. That's the definition of porosity, okay? And you could compute this porosity at the current configuration or at the current state. And when we refer to variables that are defined corresponding to the current state, we call that an Eulerian variable or Eulerian variable, and because of that, also this one is going to be an Eulerian porosity, because it's at the current state. It's defined at the current state, okay? It's always. So I tell you what is the volume of the pores and what is the bulk volume, I can compute porosity right away, okay? However, we're not going to use that porosity because it's going to be more convenient to our formulation to utilize another porosity, okay? If I wanted to compute the pore volume, and where the bulk volume is this, and the original is that one. If I wanted to compute the pore volume at the current state, what should I write? Now I'm asking you for an equation with variables. So do you agree with me that we should write the porosity, the Euler porosity, times the bulk volume, right? That's going to be the pore volume. But also, I could write that porosity as, and this is the definition referring to the original volume. And the variable that is going to make that equality to be true is phi, which is called the Langrangian porosity. And that Langrangian porosity, if we just work out this equation, is going to be the porosity or the pore volume at any time t divided the original bulk volume. So if you see, it's not a porosity, it's a porosity that depends on the original volume. You have a question, John?
Are these all scalars?
These are all scalars. Yeah, these are all scalars. So we're dealing with volumes, porosity. These are all scalar. So let's write that down. So this is pore volume at time t, and this one is the original pore volume. And we're going to define also a variable phi, which is going to be the current Lagrangian porosity minus the original Lagrangian porosity, and this variable is going to be called the change of porosity. Yes?
Isn't that denominator not the original pore volume, but just the original volume?
Correct. The original bulk volume. Thank you for that. Is the original bulk volume. Okay? So we have defined now two new variables. The Lagrangian porosity and the change of porosity. And now we're going to see how this is useful to us. Okay? And in order to do that, I'd like that you consider two examples before we get into the equations, just to see that this actually makes sense. Let me take advantage of this space I have over here. If I want to make a change of the bulk volume, how can I make that change? What can I deform in order to make that change? We could change the pore volume, but we could also change the volume of the matrix, the solid matrix, right? So if I want to change that total bulk volume, I can introduce a solid strain, and this is going to be the strain of the solid, not the bulk volume, that we're going to call epsilon s, where this epsilon is not the same as the epsilon I have been writing before. This is going to be equal, with that epsilon, I mean volumetric strain. Okay, so instead of writing volumetric all the time, I'm going to use this type of epsilon. And so I could introduce either a change by modifying the strain in the solid, or also I could introduce a strain by changing the porosity inside the porous solid. Porosity or change of porosity by itself is not a strain, right? It's a sort of a change of porosity just. But if I wanted to convert this into a strain, what would you do? What is the definition of a strain? Okay, so what would you divide this change of porosity? The original Lagrangian porosity. And that's going to be a porosity strain, okay? So this one is a solid strain, and this one over here is a porosity strain. Okay, so let's work through the equations. And we're going to define this epsilon s, which is the strain of the solid. By definition, the strain of the solid, in order to define that, I need a volume of a solid. And a volume of a solid is going to be equal to 1 plus the strain of the solid times the original. Let me move this s to the top so I don't have to put those subindices next to each other. But this is just the definition of this guy, right? By definition of a strain, is a coefficient that plus 1, you multiply the original volume, you get the actual volume. That's just the definition. But we don't want to work with solid volumes. We want to work with bulk volumes because we want to work with porous media. And in order to do that, we're going to get rid of these S subindices here. And at any time t, according to our definition over here of Eulerian porosity, the volume of the solid is just going to be 1 minus n, the volume of the porous solid at any time. This is just the same. And the volume of the solid at time 0 is going to be 1 minus Langrangian porosity. And further, this is going to be the original porosity, Langrangian porosity, divided times the bulk volume. So now we have gone from a solid volume to a bulk volume. And also, I do not want to work with this Eulerian porosity because I'm going to find later on that it's much more convenient to work with the Langrangian porosity. So I'm going to get rid of this n. So this n, according to this equation over here, is porosity times that one divided this one, and that times all of this. So I'm not doing any change whatsoever respect to the previous equation. And I'm going to do one more thing over here. What is this guy? Can you recognize this one? I hear volumetric. Volumetric what? So if I now talk, these are bulk volumes, right? These are all bulk volumes. What is the definition of bulk volumetric strain? This is going to be like that, right? It's the same thing as that one, but now with bulk volumes. So this guy is actually going to be, if I put it over here, no, this is wrong. This is wrong.
I'm pretty sure it's backwards.
Yes, Yes, yes. It's like that. So new at time t divided original, okay? So when you do that, you will realize that now if I put that equation in here, I can write this one as this, and here I'm going to, let's see, what did I do here? So I have the d omega, and oh, let me say one step over here too. What is, you see that we have these two guys over here too. So with the same equation, I can also write this one divided by plus that one is going to be also 1 plus the volumetric bulk strain. So I'm going to end up with this equation. So this one comes from the squares over there. 1 minus the porosity. And if you do the common denominator over here, you will see that, so common denominator of this, then it's going to be 1 plus this minus the porosity, and this is going to be 1 plus the solid volumetric strain, 1 minus porosity 0, and after you equate a little bit more, I like to find out what this guy is, and I get the final equation that the volumetric bulk strain is going to be 1 minus porosity. I'm just changing the order, okay, of this. Multiply by this guy plus, if I add this one to that one, you will see that this one will cancel out, and this one now is going to be porosity minus porosity, and we know that this guy is the change of porosity. So this is the final equation. We know that the bulk volumetric strain is a combination, and actually this is a very important equation, because we could also write this guy as porosity divided original porosity times original porosity. So you will see that it's actually a volume fraction equation. So 1 minus porosity times the solid of the strain plus the pore strain, the porosity strain times porosity. So 1 minus porosity, porosity. Solids, pores. And now with that, you will see that we have a lot of interesting cases in which now our solids deform, our pores deform too. So let's see some examples, just to see what would be the application of this equation, in order to remember this a little bit better. Let's imagine that we have a solid in which I put constraints from all sides, so it cannot deform. The porous medium as a bulk is not going to deform. But inside the pores, I'm going to apply a pressure P, which is high enough and that actually deforms the pores. based on the equation that we just derived, what is going to be the bulk volumetric strain? It's going to be 0. And our strain is just going to be like this. And so, therefore, from here, I'm missing that one, the strain of the solid is just going to be the change of porosity divided 1 minus the initial porosity. And that kind of makes sense. And here, you know, in poromechanics, and also to be in agreement with the book, we're going to switch conventions just for this chapter, okay? And we're going to assume that compression is negative and contraction is negative. You will see at the end we'll change back the equations to the convention that we want. But let's just develop the theory the same as in the book and using the same convention. If your porosity gets larger and this value is a positive, what this equation tells you is that the bulk strain of the solid is going to be negative. And it's going to shrink, right? So any increase in porosity is going to come at the expense of a contraction of the solid. Let's see another example. And we're going to use this example in a bit as well into another equation. Let's say example number 2. Also, we have a porous solid. And now I apply stresses from all sides. Oh, something I forgot to say, guys, about the finite element solution and in general for any continuum mechanics solution. At the boundary, you may specify either a stress or a displacement in the same direction, I mean. You cannot specify both. That will be a violation of the equation. So you either specify a stress or a displacement. For example, I could say, well, I have a stress in this direction, but I don't want the boundary to move in this direction. You can do that, okay? That's allowed because those are two different directions. But you cannot say there is a stress here and at the same time that this one is not going to move or it's going to have a prescribed displacement because that's not possible. So in your solutions, remember, you either specify displacement or a stress. So instead of now specifying a displacement, which was 0 in this case, we're going to specify a stress, and that stress, which is, we're going to call, well, we don't have to call it anything because we're just talking about porosity, is going to be a compression, but at the same time, if I didn't have any pressure, what do you think will happen to this solid? Porous solid. Well, we're still in elasticity, so there is no crashing so far. We'll get to that later on, okay? But if this is the deformable porous solid, if you apply stress, it's going to deform. And what do you think is going to happen to the pores? They're going to be smaller, right? But in this case, we're going to apply a pressure which is enough to keep the pores of the same size. So no deformation of the pores. So now if the change of porosity is equal to 0, then from this equation over here, I'm going to have that the strain in the solid is just going to be equal to the volumetric strain divided 1 minus porosity. And in this example, notice that we have done is produce a combination of stress and pore pressures such that all the strain in the bulk porous medium comes at the expense of the strain in the solid. So actually now this one is getting a compression and it's getting smaller, but the pores are not. And also very interesting in that is, for example, say that here you have a strain of 10% and you have a porosity of 0.5. That means that in order to obtain, to keep the pores of the same size, the strain of your solid will have to be 20%. So your solid will shrink 20%, but the porous solid is just going to shrink 10% because it's a combination of the two. Okay, how are we doing with time?
It's 3:08.
3:08. So we're just going then to make some drawings and we'll not get into the equations, okay? But you will see that naturally after this, we can add now the porosity component to the porous solid. So this section, we're going to call it free energy of the porous solid. There are several ways that you can derive these equations. I like this one. This is the way I learned it, and I think it's very constructive in order to explain what's going on over here. Okay, you remember that we talked about strain energy, right? If we have a solid and we add strain, we can add energy to the solid. And if we have a porous solid too, we can add energy to the solid, but it's going to come to the stresses and it's also going to come to the pressure inside the pores. So, for example, let's say that I have a solid, which is that one, and I apply a volumetric strain or stress that produces such a strain. I can quantify the amount of work added to that solid by multiplying the mean stress times the variation on the volumetric bulk strain, right? So what is this?